integrals, you integrated functions over an area, usually in the xy plane. All right, triple integrals is when you have a function of 3 variables, x, y, z, and you are integrating over, say, a cube, or you're integrating over a volume because you have another dimension in there. So it's kind of hard for us to visualize, but you're not integrating over an area, you're integrating over a 3-dimensional space because you've got x's, y's, and z's. So when you have the triple integral over a region, I'll just call the region T, of your function x, y, z, this is a dv because you're integrating over a volume, not a dA, which is where you were integrating over an area. Now, if your volume is represented by x's, say, that go from A to B, and your y's go from C to D, and your z's go from E to F. That's a lot of letters in there, okay? As long as these are all constants, you can set the method of integration up as an iterated integral any way you want to. So you could do A to B, C to D, E to F, your function x, y, z, and then this would be dz, this would be dy, and this would be dx, the way I've got it set up. But just like a function of 2 variables, when you get 3 in there, the order is important. Again, you're always integrating from the inside out. You would integrate with respect to z, then with respect to y, and then with respect to x. And again, as long as these are all constants, you can change the order up. It doesn't matter which way you go. Just make sure that these limits go with whatever variable you are integrating with respect to. All right, if you're integrating and any of these limits have constants, no, not constants, variables, I'm sorry, wrong word. If they have variables, those with the variables have got to be on the inside. And the last one on the outside has got to have all the constants with it. Okay, so those are the kind of important things you need to keep in mind. If you have a very straightforward one, if you are integrating, like number 10, if you're setting up the triple integral over the region E this time of your function e to the z divided by y dv, where E is the set from your y's from 0 to 1, your x's from y to 1, and your z's go from, from 0 to xy. Let's get this over, get right here. All right, on your limits of integration here, this one is going to have to be on the outside because it's got the 0 to 1. And then this one would need to be on the inside because you've got x's and y's. So when you set it up, just make sure you put the 0 and 1 on the outside, and then you're going from y to 1, and then you are going here from 0 to xy. You have e to the z divided by y. This is your dz, this one is your dx, and then this one is your dy. And I don't mind if you use your calculators, obviously. Do y'all want us to put this in the calculator to see what we get, or are y'all good with this? Anybody good with it? Okay, but you see how to set it up if it's just given to you. All right, the challenge comes when you are given problems, and I went ahead and wrote them down. It's from your book. Let me see if I can pull this out. Evaluate the triple integral z dv, where E is a solid tetrahedron and it's bounded by 4 planes. x is equal to 0, y is equal to 0, z is equal to 0, and the plane x plus y plus z is equal to 1. In this particular problem, you've got to figure it all out. This actually may be example 1. No, it's example 2. This is example 2 out of your book. And I'll probably set it up differently. Doesn't matter. All right, so you've got to decide your limits of integration for everything. Okay? So the first thing that I notice is I've got z is equal to 0 and I've got this plane. If I solve this plane for z, then z is going to equal to 1 minus x minus y. This plane is above where z is equal to 0 because that's the xy plane. So I can get my z's ranging from 0 to 1 minus x minus y. Now, to figure out my limits of integration for x and y, the easiest thing to do is to project down to your xy plane. Okay? In my xy plane, I know I've got x equal to 0 and y is equal to 0. So that's putting me in this first octant right here. And I'm going to use the fact when z is equal to 0, I'm going to substitute in here when z is 0, then this equation becomes x plus y equals to 1. I can graph this in the xy plane. This is the line y is equal to 1 minus x. So if I go up 1, slope of down 1 over 1, this region is in my xy plane. So this is where you set up your limits of integration, just like we did when you had 2 variables. So I would let this is the line y is equal to 1 minus x. So I would let my y's range from 0 to 1 minus x. And then x is going to be ranging from 0 to 1. So there you've got all of your 3 limits of integration. You've got here for x and y, and you've got here for z. And the z needs to be on the inside. So I do 0, 1 on the outside, 0, 1 minus x next, and then 0, 1 minus x minus y. And I'm integrating z. This is dz, this one is dy, this one is dx. Do y'all have a question about? Yeah.
I don't know where integrating z.
Oh, because that was given. Okay, that was given. Good question.
And whichever one has the most variables in it needs to be
on the inside.
I'm
not quite sure I turn off the record button.
Yeah, I want it on. I'm recording it for the 2 that aren't here today. They asked. That's fine. No, they asked me to do that. So it's just recording what I'm writing up here, not anything else. All right. Any questions about this one? Okay. All right. Here's one where we might have to do a little bit more work. This is out of your book also. This is one of the homework problems. You're integrating over the region T, the function xyz dv, where T is the solid tetrahedron with these vertices 0, 0, 0, 1, 0, 0, 1, 1, 0, and 1, 0, 1. So we actually are going to have to look at 2 graphs on this one. We are going to have to look at the graph 3-dimensional x, y's, and z's, try our best, and then we need to look at an xy graph. Alrighty, so let's just start by looking at 3-dimensional and see what we can do with that. Alright, I'm going to come out here to 1, out here to 1, and up here to 1. All right, so I've got the point 0, 0, 0. I've got the point 1, 0, 0. I've got the point 1, 1, 0. So I guess that's about right there. I'm going to label these 1, 0, 0 so I don't get them lost. And then I've got the point 1, 0, 1. Okay, so let's see what I've got here. All right. All right, it's kind of hard to see here. The way I've drawn this, that should obviously be a straight line. All right, this is a flat surface right here. The top of my tetrahedron is this that I'm shading. That's the top. It's a plane. So it comes out here, and then there's like a sheet, a plane that's on top of it. This is point 0, 0, 0. This is my XY plane. There's my third dimension. All right, this, like I said, the part that I shaded is the top of my figure. So when I'm integrating my z's, I'm integrating from the XY plane, which is z is equal to 0, to whatever this plane is up here. But they did not give me the equation of this plane, so I've got to find it. So this is where we're going to have to reach back into how do you find the equation of a plane? Well, for the equation of a plane, remember you need a point, and then you need a perpendicular or an orthogonal vector to get the equation of the plane. And the equation of the plane is a x minus x1, b y minus y1, plus c times z minus z sub 1 equals to 0, where the orthogonal vector has got the coordinates, the components a, b, c. And the point is the x1, y1, z1. So for this right here, this plane that I've shaded, we're going to have to pick one of the points, pick one of the vertices. This one, or this one. I would probably pick this to be my point. Then I need to find a perpendicular vector to this plane. To find the perpendicular vector, what you're going to have to do is find two vectors that are in the plane and take their cross product to get the orthogonal vector. So let me get my vectors. I'll call one V1. I'm going to go from here to here to get one vector, so subtract. 1 minus 1 is 0, 1 minus 0 is 1, and 0 minus 1. So there's one vector in the plane. Subtracting here to here. Then I need a second vector. I'm going to go from the origin to this point, or this point to the origin. If you subtract, that's going to give you negative 1, 0, negative 1. Those two vectors are on the surface of my plane. Now I need to do the IJK thing. 0, 1, negative 1, negative 1, 0, negative 1. And find my orthogonal vector. I had negative 1 minus 0 minus j. It's going to be 0 minus 1 plus k, 0 plus 1. So this gives me my orthogonal vector, if I did this right, to be negative 1, positive 1, positive 1. Okay, this is old stuff. I'm just pulling it back from, trying to refresh your memory and pulling it back from the old stuff, okay? So now this is my A, B, and C. I'm going to use the point that was in common to both vectors. So the equation of the plane would be -1 x minus 1 plus 1 times y minus 0 plus 1 times z minus 1 equals to 0. -x plus 1 plus y plus z minus 1, 1 minus 1, and -x plus y plus z equals to 0. This is the equation of the plane that's right there. Now I did all of this so I could find the top of this figure so I'll know to get my limits of integration for z. So now I know if I solve this for z, the top of this, z is going to be going to the plane x minus y. So my z values are ranging from 0 to x minus y. 0 being this surface down here. Right, now I got to figure out what to do for x and y. So to figure out what to do for x and y, I need to look at this shape that's down here in the xy plane. But I don't know about you, but that's too difficult for me to look at down there. So I'm going to take it and I'm going to put it over here on its separate little graph. This is my xy plane. And all I have to do to plot in this xy plane is to go back up here and plot only the xy points. So 0, 0, the point 1, 0, the point 1, 1, and then the point 1, 0 I've already got on there. So this is the triangle that is represented down here in this space. Are y'all following me? From this triangle, this is where I'm going to get my limits of integration for x and y. So I can go from this to this line. This line would be, let's see, this is 0. Y is equal to x, perhaps. Okay. So my y values are going from 0 to x, and my x values are going from 0 to 1. So 0 to 1 on the outside, 0 to x next, 0 to x minus y. My function was x, y, z. This is dz, this is dy, and this is dx. Question? So some of them is pretty straightforward. Some of them you've got more work to do than others. Yeah, Red.
Just the
Yes.
you just use the cross product on the vectors just to get the point of the equation.
I just used it to get the equation of that plane right there. That's the only reason I used it. Because you had to have, this is several chapters ago when we did the equation of a plane. You have to have a point and an orthogonal vector. Okay. All right, I wrote another one down because this one is a little different because it wants you to find a volume with triple integrals. Now, I don't know if you remember, but in a couple sections ago we did volume using an area. Volume using double integrals. You can do a volume using double integrals or you can do a volume using triple integrals. You get the same answer. They want us to use triple integrals to do this volume, which means you need limits of integration for x, for y, and for z. And when you're getting a volume, the function that you integrate is the function 1. If if you do a volume, because dv is a volume, if you do volume with triple integral, the function is a 1. That's like if you do an area with a double integral, the function is a 1. Alrighty, so if we're going to use triple integrals to find the volume of this tetrahedron that's enclosed by the coordinate planes and this plane right here, then we are integrating 1 dv. We need our limits of integration for x, y, and z. The coordinate planes means that it's limited just to the first octant. So I know without graphing that when I solve this for z, that's going to be the top of my shape. Y'all get that? So if you solve this one for z, this is 4 minus 2x minus y. Then my limits of integration for z will be from the xy plane, which is 0, all the way to 4 minus 2x minus y. Again, to get your limits of integration for x and y, you need to project down to your xy plane, which means in this equation, z is 0. So in the xy plane, z is equal to 0, so we have the equation 2x plus y is 4. Solve that, y is negative 2x plus 4. Slope of 2, so down 2 over 1, down 2 over 1. Here is the line. So y is negative 2x plus 4. So using this picture, I would let my y values go from 0 to negative 2x plus 4, and my x values would go from 0 to 2. Now I'm trusting my graph because I counted it off, I counted my slope, but if you're unsure about this, solve for it, see what x is if y is 0. So if y is 0 and you solve it, you do get 2. So when you set it up again, 0 to 2 on the outside, 0 to negative 2x plus 4, and then 0 to 4 minus 2x minus y. I'm looking for the volume, so the function is 1. This is dz, this is dy, and this is dx. Now, if we have been, let me just point out something. If we had been back a couple of sections ago and they had asked for the volume of this, and I don't know which section that would have been, if we had used a double integral to do this for the same problem, then you would have gotten your limits of integration for x and y just like we did. We would have integrated from 0 to 2, and we would have integrated from 0 to negative 2x plus 4, and then we would have integrated our function, which is 4 minus 2x minus y, and this would have been dy dx. And that's what we would have done a couple sections ago. You could have had the exact same problem, and you would get the same answer both ways, because it is a volume. Okay.